Okay, thank you everyone for being here. It's a pleasure to be here to tell you about our breakthrough distance observations at Parkes of Proxima Centauri. So I'm sure I don't have to tell anyone in the room here that we are in this amazing, extremely exciting golden age of exoplanet discovery where every week there's some new fantastic thing found. And I think it's the perfect backdrop. There has never been a better, more compelling time for us to be asking the question, are we alone here in the universe? And that's where the Breakthrough Listen program comes in, and Andrew introduced this earlier, and so I'll just keep it brief and say, in the words of my colleague, it's the Apollo program of SETI. Very briefly, there are three main components. There's a survey of the million nearest stars. There's going to be a survey of the Milky Way over the galactic plane, and then we also want to see around the closest 100 galaxies, so we have a good sampling of the possible parameter space, and we want to make all of our data that we can publicly available. So it'll be a very large public astronomy data set that people can mine through and look for either other science or help us find the SETI signal that we're looking for. So traditionally, SETI has been done over the the waterhole between the 21 centimeter line and the 1667 megahertz maser emission. But the radio window that we can probe here on Earth is much larger. And here, this graph shows atmospheric opacity, where are we, as a function of wavelength. And so the 21 centimeter line is somewhere around here. We've done some searches there already, but there's a lot more parameter space. And really, to do the most comprehensive survey we possibly can, we want to do as much of the parameter space as we possibly can. So we're looking for things, and in this particular talk, I'll be talking about Proxima Centauri, and we know the distance there. It's 4.25 light years, and so we can ask the question: what could we feasibly see? And we have to be very careful to not put a kind of anthropocentric bias on, but it is illustrative to see with the technology we have today, what could we possibly see? So on the scale of less luminous to more luminous, there's things like high-power TV and radio. More luminous than that, again, is aircraft radar by about 5 orders of magnitude. And by a few orders of magnitude on top of that is planetary radar, where you send out a signal of maybe up to a megawatt, bounce it off some asteroids or near-Earth objects, and look at the scattered wavefront. So we use up to about, with high-power TV and radio, about 10 to the 5 watts. EIRP is equivalent isotropic radiated power. So if something is directive, if you have an antenna that has gain in a particular direction, and you wanted to convert it into an isotropic power, this is what the EIRP does. It's just the actual power times by the gain of your antenna. So for example, the antenna that's picking up the signal here is over there, a log periodic dipole array. That's got a gain of probably about 10. Something like Jodrell Bank down in the corner, or the Parkes telescope has gained more like 1 million. Aircraft radar has higher gain, and so you see a higher number come out. It's also got a higher power transmitter, so 10 to the 10 watt, and brighter again is interplanetary radar. So just looking at what we could see with the technology we have, Parkes, the 64-meter dish, could detect Arecibo's interplanetary radar from across the galaxy, kiloparsecs, within a few minutes. And it could also make a 10 sigma detection of a narrowband signal. The signal type is important, from Proxima Centauri with an EIRP of about 10 to the 10 in about a minute. So it is feasible, even with single dish telescopes, without going to the next generation of telescopes, that we could detect a signal, particularly from stars as close as Alpha and Proxima. So I know it's toward the end of the day. I promise this is the only formula I have here. Just giving you a brief introduction to why SETI searches for narrow bands. So a telescope sensitivity in radio often uses this system equivalent flux density, SEFD, which is a measure of the collecting area of the telescope and the temperature, the amount of noise introduced by its analog electronics. And to make a detection, you have to have a detection threshold, and you also, it depends how well matched your channel bandwidth is to the signal you're looking at. If you're looking for a narrow band, so a continuous wave signal, you can get a very good, because this is on the top here, the smaller it is, the better your sensitivity. Similarly, if you integrate for longer, have a longer time on sky, you can get the sensitivity down that way as well. Conversely, if you have a very narrow, a signal that is narrow in time, so a pulse, they are intrinsically wideband. So if you want to look for those, you can't use spectral data products with very fine resolution. You have to use a different data product. And so just to show you two examples, and these are just on opposite ends of the kind of parameter space. You have very narrow band. This is Voyager that we took with green bank. So you can see the telemetry signal here. On the other side of the plot is narrow in time. This is a pulsar, which Matthew Bales will probably talk more about. But you can see here, this axis is in megahertz, and the size of these is in hertz or kilohertz. So to show you some breakthrough listen data very quickly, and I don't want to spend too long on this, this is 66 million channels. You can't see Voyager there until you actually zoom in on it. It's over there. And it really shows you SETI is a needle in a haystack search in that the parameter space is so massive. And so you need to make sure that you can firstly get down to the resolution so you can get the sensitivity. You need to have the bandwidth so you can cover as much frequency as possible with one pointing, so you've got a high survey speed. So it's technically challenging. This is also only one of about 16 banks that we have at Green Bank at the moment when we did this observation. So you can even zoom on this further and you can see some interesting telemetry information there. And if you want to download this data and play around with it, there is a little Jupyter notebook that you can go through and play around, and it's a little bit of fun. You can download that from our website. Okay, now moving on to Parkes, and this is Parkes over here, oriented the right way with the galactic plane, nice and flat. Parkes is a 64-meter aperture telescope. It's been around since the 1960s, famous for collecting telemetry from the walk on the moon. It also has done SETI in the past in Project Phoenix in the 90s. We're using it mainly for breakthrough listen. It has a multi-beam receiver which has 13 beams, and that gives it a very fast survey speed. So you want to use that to do a survey of the galactic plane, and we'll focus with Green Bank on the 1709 star sample that Howard Isaacson has a paper about. For Southern Hemisphere sources, it's useful to have a telescope in the Southern Hemisphere. So for Alpha and Proxima Centauri, we can only observe those with Parkes. So this plot here is showing the minimum detectable EIRP, isotropic radiated power, with Parkes. And so Parkes has a SEFD of about 30 Jansky at a gigahertz. And what these lines are showing is these are lines of constant EIRP. So if you had a very big transmitter, you don't need as much power. So for example, an isotropic source here would appear the same as if someone transmitted with a 100-meter dish with much less with this is a kilowatt, whereas this is a much higher number, which is harder to send out. So the reason I'm showing this plot is to say that Parkes could easily detect a targeted transmission from a technologically similar civilization to ourselves, but that we couldn't detect the so-called leakage where they're not deliberately transmitting to us. However, future telescopes could. Now, I don't have time to really take you through the instrumentation, so I'm just giving you a 30-second overview. There's a receiver that sits at the top of the telescope. There's a whole bunch of analog systems. And then we have the breakthrough listen backend that we installed, which is a FPGA front end and a whole bunch of servers with lots of disks and graphics cards in them for data analysis and storage. I don't have time to go through this at all, but apart to say that this is our system on the right, and this is the regular Parkes system on the left. So we have a kind of bring your own philosophy where we bring our own digital instrumentation, our own kind of SETI toolkit, and reuse existing infrastructure. The current capability at Parkes is about 1 gigahertz of bandwidth that we can record to disk. We want to get that up to about 5 gigahertz of bandwidth so we can capture all of the multi-beam. And as was mentioned, we store 3 different kinds of data products. We have a narrow time resolution and a narrow frequency resolution product for searching different parts of the parameter space. Okay, so getting into it, we do some observations of Alpha Centauri with Parkes. Every time we did an observation, we looked at a calibrator, a pulsar, which we just use for checking that our systems all look nominal, because if you have something wrong, it's hard to detect them. And then obviously we looked at the stars of interest. So one thing you have to do is remove the bandpass from your signal. You have to remove, I guess it's like the telescope transfer function. So you can remove that with some kind of high-pass filter or by calibration on a flux standard. And then you look for events, narrowband signals that you can consider a hit. If you see that on and off source, it's, as Jerry said, it's like a lens flare. There's radio interference coming in from your side lobes. So here, there's 3 hits, but all of these would be discarded because they appear in a reference spectra and an on spectra. Here, alpha and Proxima are the on and the off. Another way you can look is by looking at different things. You don't have to look at the power per se. You can look at things like Ptosis, and then you see signals pop out. Showing the actual transfer function here, or the bandpass over, this is an S-band observation of the 2 sources. You can see there's a bit of a difference in power level, but apart from that, you can't really see anything interesting. Here's one where I've actually done a calibration using a flux standard, and you can see that there's some instrumental systematics like this standing wave. There's also some other interesting things in here. There's the local oscillator that powers the down conversion system. You can't do much about that leakage. That's self-generated. The 21 centimeter lines blaring right through there. GPS L3, which is used for nuclear detonation detection. And to show this is a dynamic waterfall plot where I've removed the mean, removed the bandpass. You can see here's some interference, which we would get excited about if it weren't for that. It's also in the on and the off source. So we discard this as very strong RFI. And just to recap, this is frequency along this axis and time in MJD on the other axis. To show a hit that's interesting, and I won't say it's anything more than interesting. Here's some data where Proxima Centauri is on the left, Alpha Centauri is on the right. There's something, a narrowband signal that kind of popped up for a short period of time and then wasn't on the off source. So we think this is an interesting signal. We want to know more about it, but it's probably a satellite moving through the side lobes. One reason I think this is that the width here is about a minute, which is probably how long it would take to cross through the side of the telescope. Showing the on and off, similar to what Andrew showed, except now this is time is on this axis. I've just taken a frequency slice, and then flux is on this axis. You can see that it wasn't on the first observation, it wasn't in the reference, then suddenly it was there, wasn't on, and was. And so this is the kind of thing, so in Emilio Enriquez's paper that we've just submitted, we have 11 such events, which are just as compelling as this, but they are probably still RFI, so we're not getting too excited about this. I'm running out of time, but just to say we are observing other sources. The 2 main that we've observed are Proxima Cen, Alpha Cen. We're also looking at these J sources are pulsars, which are used for system diagnostics. The other sources are calibrators, and M62 was for a special project we worked on with William Edmondson. And just finally, to say a few words about the future prospects. We are really excited to use the next generation of telescopes such as Meerkat because you get a big boost in sensitivity. And the SKA is particularly interesting because it could detect about a light bulb's worth of power from an Arecibo-sized transmitter. And just to show on a graph, that's this line here, and that's about 100 watts. So to conclude, we have some interesting things in our data. I won't yet say it's compelling, but we're continuing to look. We'll use a similar methodology to Emilio's paper that came out today. The methods we have when we eyeball data such as this all fold into the pipelines where we'll look through all the data. There's some next steps for moving forward, which I'll just leave up here, and say that we'll continue to monitor for a long period of time as the program progresses. So thank you.
So are there questions for Danny about these observations?
Ron?
Ron Akers. Why am I not surprised?
Thank you. Nice introduction, Danny. As you said, and Andrew also said, you've got these tantalizing signals which are probably RFI. Now, by definition, a SETI signal is going to look like RFI because we are intelligence and we made the RFI. So you've got to use something a bit more clever than an on-off to find out whether it's real or not, because these are intriguing, but you'll never be able to say, we're sure this is coming from Proxima Centauri. So you need positional information. Can you comment, and Parkes in fact could have provided that, because it has simultaneously more beams, but you're not using them. Can you comment on what the future prospects are for measuring the positions from which these signals come from? Because otherwise we can never be sure.
Sure. We do want to use all the 13 beams of the Parkes multi-beam receiver. We're going to be installing some more hardware in the next month or so that we can do that. We have an RFI expert, Greg Helborg, on hand, who's going to help us do the analysis so we can use the spatial information you get from the multi-beam to remove those data. But there are other ways we can look at it as well. Because we can record the raw voltages, we can, when we create our spectra, if we find candidates in real time, which is another thing we're working toward, we can extract just the small areas and do a downsample to get some raw data just around interesting parts of the spectrum.
Additional questions? Yeah.
Danny, are you? I hope you're aware that our colleagues in India at the GMRT have developed a database and a software package of the satellites that emit radio radiation within certain bands that actually affect the GMRT. And this might serve as a first indication of whether what you're seeing is actually satellite interference, and so at least assist in that process of filtering the various RFI signals that you see.
Yeah, we definitely need to use information such as that. We have a student project where a student is going through and building up a database as well, so we'll have to cross-match those two catalogs.